What we designed the system for is actually to be able to withstand the extreme max in terms of cold, so minus 40, minus 45.
10,000 research and manufacturing jobs could land in Canada if Ottawa adds the Swedish fighter jet to its military fleet.
The Gripen E operates with a new agile architecture system, which allows the aircraft to be upgraded with new tactics and new capabilities seamlessly.
The Gripen E isn't just another fighter with a fresh paint job and a longer brochure. The whole point of this aircraft is that it's built around an agile, modular architecture, so upgrades don't feel like ripping the plane apart every time a new tactic, sensor, or weapon shows up. It's designed to evolve fast and fold in new capabilities without the usual years-long pain. And for a country like Canada, that matters more than people realize, because the battlefield isn't just airspace on a map, it's the climate itself. When you're operating in the far north, cold isn't a background detail. Cold is a system-wide stress test. That's why the story starts with temperatures, not politics. When engineers talk about designing for the extreme max of cold, they're not being dramatic. They're talking about the kind of temperatures that don't just make you uncomfortable, they change how metals behave, how lubricants thicken, how fuel flows, how seals shrink, how electronics respond, and how quickly a jet can go from parked and frozen to ready to fight. We're talking minus 40, minus 45, and worse. Those numbers don't just affect convenience, they affect readiness. And readiness in an Arctic scenario is the difference between being first in the air or being forced to watch an unknown contact move through your space while your systems are still waking up. Now add the industrial side. The moment Ottawa even seriously considers adding a Swedish fighter jet to its fleet, the ripple effect isn't small. We're not talking about a handful of maintenance jobs. We're talking about the kind of technology transfer that can anchor a serious domestic aerospace footprint. Saab has been clear about its willingness to transfer technology and support local building. If that plays out at scale, you're looking at the possibility of roughly 10,000 research and manufacturing jobs landing in Canada, and not as a vague promise, but as the natural consequence of assembling, sustaining, and upgrading a fleet over decades. That kind of long-term work builds skills that don't disappear when a single contract ends. But the technical heart of the story is what happened in Derby, at the Rolls-Royce test complex, when most of the world was asleep. The lights don't go off at a place like that, but there are still moments when the atmosphere changes. One of those moments hit at around 3 a.m. on a Tuesday, inside a climate chamber designed to recreate environments so punishing that bad weather sounds like an understatement. This wasn't a simple cold room. This was a controlled torture chamber for machines. Temperature locked down at about minus 52 degrees Celsius, conditions simulating 40,000 feet, Arctic wind chill recreated through airflow systems that cost more than many frontline aircraft. And on the test stand sat a next-generation turbofan with documentation tied to the Royal Canadian Air Force. It was wired like a patient in intensive care, hundreds of sensors tracking combustion stability, lubricant viscosity, fuel atomization, thermal expansion, and stress tolerances across a savage temperature spread. The goal wasn't a small improvement, it was proof that the engine could reliably perform where many engines struggle to function at all. Then the sequence began. From a fully cold-soaked state, without preheating systems or auxiliary ground equipment, the engine ignited and climbed to stable combat thrust in 93 seconds. Not eventually, not after a careful warm-up, 93 seconds from inert frozen metal to usable thrust. That number is the kind of thing that doesn't stay inside engineering notes. It travels, quietly at first, then everywhere. In defense circles, it becomes the stat people repeat in closed briefings because it forces uncomfortable comparisons. Under similar minus 45-degree testing conditions, comparable American alternatives have been reported to average around 14 minutes to reach operational readiness and to suffer meaningful thrust degradation early in the cycle while critical systems stabilize. That isn't a cosmetic difference. In cold weather air combat, it's the difference between intercepting on your terms or chasing on theirs. And it didn't stop at one dramatic start. The extreme environment trials reportedly ran for more than 400 cumulative hours, documenting repeatable cold starts, sustained thrust output, and structural durability across rapid temperature transitions. Once pieces of that performance story started leaking into defense networks, the reaction wasn't public outrage, it was quiet recalibration. Because if the gap is real, it represents an Arctic performance disparity that changes how planners think about northern air defense. Here's the part most people miss. This isn't just about an engine being strong, it's about the industrial logic behind it. Rolls-Royce didn't chase this development only to check a contract box. It's a targeted answer to a known limitation in conventional turbofan design. For decades, many engines have been optimized around high temperature efficiency and cruise performance, accepting compromises in deep cold behavior because most air forces rarely live in that world. That trade-off is fine if your reality is temperate runways and predictable logistics. It's not fine if your sovereignty patrols run over the Arctic archipelago, where winter isn't a season, it's a permanent operating condition. The breakthrough begins in a place that never makes headlines: lubricants chemistry. Traditional aviation lubricants thicken drastically as temperatures plunge. That thickening increases friction, delays spool up, and puts heavy strain on starter systems. It also increases wear at exactly the moment you need reliability the most. The new formulation described in this story is meant to maintain stable viscosity down to around minus 60 degrees Celsius. That's the kind of detail that sounds boring until you realize what it does. It allows internal components to rotate freely without external heating, reduces stress during ignition, lowers wear, and removes one of the biggest causes of cold start delays. In other words, you're not cheating the cold with extra equipment, you're designing around it. Fuel behavior is the next trap. At extreme cold, fuel can form wax crystals that restrict flow and compromise atomization. Many designs compensate with preheating mechanisms, which adds complexity, weight, and maintenance demands at remote Arctic bases. The approach described here is more elegant. Redesign the injection system so spray patterns and droplet size remain optimal at low temperatures, preventing crystal accumulation without energy-hungry heating cycles. That means fewer failure points, less weight, and less equipment dependency at forward Arctic locations. Then you hit material science, which is where cold becomes brutal in a different way. Many turbine alloys are optimized to survive sustained high heat, but can be vulnerable to microfractures under thermal shock, especially after prolonged cold soaking followed by sudden ignition. That's exactly what Arctic ops look like: aircraft sitting in deep cold, then being asked to go from frozen to full power fast. The response described here is a new alloy composition that can tolerate swings from roughly minus 50 degrees to plus 900 degrees Celsius without structural degradation. If that claim holds across real service life, the implications extend beyond fighters into industrial turbine and energy applications too. Each innovation on its own would be meaningful. The real advantage is how they stack. Stable lubricants help the engine spin freely. Improved fuel atomization supports clean combustion. Shock-resistant alloys preserve structural reliability through repeated cycles. Put them together, and you don't just get an engine that starts faster, you get an engine that can deliver rated thrust immediately, without a long warming window where the aircraft is technically alive, but not tactically ready. Now picture an Arctic alert scenario. Long-range radar detects unidentified aircraft moving toward Canadian airspace. The timeline matters. In one reality, your engines need 10 to 14 minutes to stabilize. In the other, you're at stable thrust in 93 seconds. That gap decides who gains altitude first, who sets the geometry of the intercept, who gets the first quality track, and who forces the other pilot to react. Add long-range air-to-air weapons like the Meteor missile, and minutes become the whole fight. And this is where comparisons start to bite. Parallel testing under identical environmental controls is described as including the F-35 with the F-135. The F-35 remains a monster across many mission profiles, but the cold start averages and early cycle thrust behavior under deep cold, plus reliance on specialized tools not always available at improvised Arctic strips, highlight a real disadvantage in that specific northern theater. Public messaging, of course, tends to emphasize the broad performance envelope. That's normal. Internally, planners don't have the luxury of comforting phrasing. They care about whether the jet launches when the North is trying to freeze it to death. What makes the Gripen angle even more interesting is integration speed. Saab built the airframe around modularity and future evolution, which means the engine upgrade path is not a full redesign. The claim here is that the updated power plant could be folded into Canadian production with minimal structural modification, with timelines measured in weeks and months, not years. That matters because deeply integrated platforms optimized around a single engine spec can become trapped. Even if a better solution exists, the certification and integration cycle can take so long that the fleet spends a decade living with yesterday's limitations. For Canada, the Arctic isn't a special case, it's the core case. Sovereignty over the Northwest Passage isn't a slogan, it's logistics, persistent patrols, remote forward operating locations, and winter temperatures that punish readiness. If Canada fields an engine that has genuinely been validated across 400 hours of extreme trials, the Royal Canadian Air Force gets year-round operational certainty instead of seasonal capability. That removes the assumption that winter creates predictable surveillance gaps that others might probe. And then there's the human factor. When pilots operate from austere Arctic strips in real conditions, they build skills that simulators can't fully reproduce. Managing rapid cold starts, dealing with thermal transitions, navigating areas where magnetic anomalies can complicate systems, operating